and we'll go through kind of we won't go through every single line of code, but we'll go through the parts and try to match them with the theory that I talk about, and how or why we chose these certain patterns to accomplish something. So I will start with, so I assume that since you're here at a machine learning meetup, you've probably seen this website or this blog post by Andrew Karpathy, and I think it's called something like the unreasonable effectiveness of recurrent neural networks, and I stole this picture from that site. But I think it's a nice picture to start with because it separates mentally the kind of paradigms of neural networks based on the types of inputs and outputs that you're interested in. So, I mean, it might be a bit self-explanatory, but the one-to-one is the traditional feed-forward neural network. So this is basically, one example is image classification, which is, I mean, just because it's the most simple in this paradigm doesn't mean it can't be complex. Basically, what it means, though, is that you have one size input and one size output. So the example here is you have one image. The images are always the same size. If they're not, you first scale them. And then you have one output, so it might be one of 1,000 ImageNet classes. One to many, you still have a static shape input, so it could still be an image. But then now we have multiple outputs. So a good example of this is image captioning. So here you have one image again, but the output is words describing what's happening in the image. Many to one is flipped around. You have, for example, a movie review, and you want to summarize that into a single output. So, for example, sentiment analysis, if it's positive or negative. And then there's two kind of ways to see many to many. The very last one, you can see as slot labeling. So, for example, this could be seen as part of speech tagging. Every single word in the input, and you can have multiple words, results in a label, one per word, so the part of speech. But the thing we're going to specifically talk about is this many to many, where you have some variable number of inputs along a dynamic axis, and you have some variable number of outputs, and they don't have to be the same. So this is basically the very high up view of sequence to sequence. So first, some background. They're relatively old and when it comes to neural network stuff, since it's moving so fast these days. So from 2014 is the first kind of description of sequence to sequence in the context of machine translation. And in fact, now I think maybe 6 months ago, 2 months, both Google and Microsoft their machine translation systems to sequence networks from the old phrase-based translation. But it's a pretty clear fit for a number of different applications. So for example, automatic text summarization. It used to be you would score a bunch of sentences and then you would extract the most salient ones and stitch together a summary, which was always clearly not from a human. But now, all of a sudden, you just plug in the data into the same sequence-to-sequence network that you do translation with, and you can have really nice abstractive summaries. Word-to-pronunciation models is what that's the example we're gonna go through today. And so here, you basically have an input sequence of characters, and it will output phonemes. So these are the smallest sounds in a language. And it'll tell, so basically the idea is to have an unambiguous representation of how you pronounce a word. And then there's a bunch of other ones. So now let's talk about the basic theory. First, who thinks or has worked with or at least understands recurrent neural networks, what they're all about? Who doesn't actually? It's okay to be shy. You don't have to be shy. Okay, so let me actually just quickly give a simple overview of what a recurrent neural network is. Basically, it's a network that's designed for sequential data, and what it means is you share parameters for each data point. So in an image classification network, you put through one image, and then you put through a second image, and the first image should not affect what the network does for the second image. They're completely independent. But with sequences, you know that there should be some dependence. So for example, it's obvious in language models, if you have the word to, then the is very common afterwards. And basically what an RNN does is it adds a loop to a neural network. And so basically when you unroll that loop, you are passing in a piece of data, and every time you go through it, you can think of it as calling some step function. And it's updating some internal state, H, which stands for the hidden state. So the hidden state keeps on being updated. So in math, the hidden state at time t depends on the input and also the previous value of the hidden state, so at time t minus 1. And then in CNTK, for example, or in pseudocode, it basically comes down to h is updated with the old value of h. And that's basically what an RNN is at a very simple level. So let's go back to what a sequence-to-sequence network consists of. So there's two pieces, basically. One is an encoder, and both of these pieces are recurrent neural networks that are stitched together. The encoder's job is to basically form some representation of the input that's then passed to the decoder. And the decoder's job is to take that representation and generate words or letters or any sequential data that your network has learned to generate. And so in the most basic setup here, we run, so imagine this is a machine translation task. We run each word through the recurrent neural network. When hello goes through, we update the hidden state. So now it has some new value. Now how goes through, we update the hidden state given what it was before. And so you can see that even without having to explicitly depend on n-grams like we did before in NLP, no matter how many times you push new data through the RNN, everything that happened back into the past up to some limit of infinity really, will have some effect on what the hidden state's value will be. So we pass this data through, we have some hidden state, then we pass the hidden state to the decoder, which is a new RNN, and we start generating words. And so I showed the kind of, you can think of it as an API of an RNN before, and what it does is it creates a new hidden state value given the current hidden state and some input. And so we need some input to start generating words from the decoder, and so we train the network to understand that when you have this special sequence start token, that it generates the first word. It knows here to generate hello is because somehow it's learned to store in its representation hello was the first word. And once we have this S, it knows, okay, now I need to generate the first word. So what is then this thing that I've called a thought vector? Basically, it's a vector representation of some data. What's happening here is that the network learns over time that as words get pushed into it, the parameters are adjusted such that we have some representation. And then that representation, which is the final hidden state of the encoder, and sometimes referred to as a thought vector, is used to initialize the decoder RNN with its initial hidden state. So, you know, as I showed, every step you're updating this hidden state H with the current input and its old value. And there's no old value, right? You need some value there. And so what happens is that the decoder's initial hidden state is the final hidden state of the encoder. So that's sequence to sequence network at a super, super high level. Did it sort of make sense so far? Yeah, I'm seeing some nods. Okay. So I just showed this slide a minute ago to show kind of how the RNN works. But in the sequence-to-sequence encoder, I talked about how it builds up this hidden state. Then we set up the decoder RNN, set its initial state, so its initial H, to the final hidden state of the encoder. That's the thought vector. We pass in this special sequence start token to prime the decoder to generate its first word. And then it generates hello. We pass that as the input to the next step. So this is kind of, the decoder is a language model. And as it generates words, those become the history of the language model. So you can see the thought vector as being an additional context for a language model. So in this view, I say, okay, so this is some pseudocode of how a decoder might look like. So we've already created an encoder. We've run the input sequence through the encoder. So we've created a bunch of hidden states at each time step. Thought vector will be the last hidden state. So the hidden state after the final word from the input sequence has passed through it. Then we create a decoder function. So we call our special RNN class. The initial state set to the thought vector, which is what I explained. Then I created a dense layer. So this is another function. And our first output will be a dense layer of the output of the decoder when we pass in the special sequence start token. Then the second output will be the same, a dense layer of the decoder given this first output. And this would continue on. And of course, you wouldn't write it like this. It's just illustrative. And so, like I said, it's like a language model. But whereas a traditional language model, you're trying to model the probability of the next word given all the words in the past. And of course, we can't do that for a lot of reasons. So we simplify it, sometimes use trigrams. And we look at a whole bunch of word counts and use some clever smoothing. And we say the probability of this word given these two words is equal to what we've calculated by looking at a whole bunch of data. But here, it only knows the words, so it's very general. And a sequence-to-sequence network needs to be very specific. And so now, we've got a posterior probability distribution over all the words. And it's basically the probability of a word at this current point in time, given all the words that have passed through, and the context, which is the thought vector that was built up by the encoder. Make sense? Yes. Yes. Yes, for sure. How many words to generate? Yeah, so we add into the training data, I think I had it, yeah. So in the training data, we have a special end sequence token. And so you typically will give some maximum length or until you hit the sequence end token. And so it learns basically that once you hit the end of what should be a good output sequence given the input sequence, it will generate this sequence end token. And then you know to stop decoding. Or at least you can keep decoding, but then in processing cut out everything after the sequence end token. Are there any other questions before I continue? Okay. But there are some obvious problems with this setup. I think it should be pretty clear that as the input sequence gets longer, you're trying to stuff more and more information into that one thought vector that's supposed to represent your entire input. And the other issue is that at each step, the hidden state H is getting updated with the most recent word from the input sequence. And so it's kind of biased towards the very last word. It has kind of the last say, if you will. So there had been some hacks to try to help with this, specifically for machine translation, at least in languages that run the same way. So for example, English and French, you would run the encoder backwards. And so the first word in the input sequence gets the last say, and then you have a stronger connection to generating words right away that were from the start of the input sequence. And then, although you would think, oh, well, I still have the same problem, just happens later, you get the benefit of the language model. So once you've already generated something like, hello, my name is William, it might, then you don't have to concentrate as much on the context. You can kind of use the power of the language model to help you more. But more systematically, there's a direct way to deal with this, and that's attention. And so here, I'll talk about what attention, or how it's implemented, what it is in a second, but first I'll show a couple graphs of what it basically does. So here is translation of English to French, and you see that although it more or less goes, the words appear roughly in similar places in the sentence. For example, was signed in English, été signé, turns into 3 words in French. And so when you're generating this word, you don't want to just pay attention to a single word in the same spot. You want to learn where in the input you should focus on when you're trying to generate your translation. This, for example, so here is some examples from the model that we're going to go through just in a minute. And you can see that, so this is the input, this is the English word, and these are the sounds that tell you how to pronounce it. So when you have PSY followed by a C, it's a psi sound, so psychology. But if it's followed by an L, it's a S sound, so it's psyllium. And here you can see that this IH had to concentrate on all 4 of these words to know what sound it should generate. And the same thing here. It only looked at this first one because, well, presumably following the K, it knew that it had to look in this particular area on the encoder. So the idea behind attention is that instead of requiring all of the input sequence to be encoded into one vector and passed at one time, you learn to focus on different pieces of the hidden states in the encoder for each word that you're generating in the decoder. So the nice thing about this is that each decoding step can directly use information from the encoder. So you keep how the hidden state was at each step in the encoder. All of the hidden states are available to us instead of just the final one. And the decoder learns which hidden state or weighted sum of states for a soft attention, given the current context and input to use. So there are many models of attention. The one that we use in this model is pretty straightforward. You basically get a representation of the hidden state. So each of the encoder hidden states for each of the time steps. So after you've put in each word, the current value of that hidden state, plus the current value of the decoder hidden states. And then you basically run a nonlinearity, you put it through a softmax, and that softmax gives you a probability distribution over those hidden states in the encoder. And so then basically what you do is you just get a weighted sum of all the encoder hidden states, and you add that to your current hidden state for your decoder, and then you have information that's targeted for what kind of piece from the input you're currently outputting. So, deep sequence to sequence, since we're talking about deep learning, there's always got to be layers. So we typically will add multiple layers of RNNs to the encoder and decoder. So you might have 2 layers of RNNs for your encoder, and then those top hidden states are the ones that you attend over, and 2 layers of decoder as well. We'll skip that. So this is, I can share these slides afterwards. This is just talking about that you could take the most probable word at each step when generating your output, or you could try to kind of get the optimal output. So if some word is very likely at the first step, but then at the second step, many words are not nearly as likely, and it would have been more likely to choose a less likely word first for the global probability, then there are ways to do this using some heuristics like beam search. Okay, so we're going to go through an example implementation of sequence to sequence in CNTK. The data will be these English words broken into graphemes, so letters, and then how to pronounce the words in phonemes, so we'll output phonemes. This is what the network looks like. Using CNTK's cool graphing function. Yeah, okay, so while I move over to that, are there any questions about kind of the overall structure of sequence to sequence? No? Okay. Oops. 1 second. There. Okay, so this is a tutorial you can find both on GitHub, and also if you have downloaded CNTK, then you have all these tutorials. Now you can also have a direct insight into some of the fights in CNTK on the CNTK team about which is the better way to do neural networks, either in a functional way or in a more direct assembly-like way. And so I wrote 2 versions of this tutorial. One is this one, which is based on a very functional approach to implementing sequence to sequence. And another one is more kind of procedural, and you can find that also on the tutorials as CNTK 599. The big difference, well, you can look into that if you're so inclined. So the example problem we're trying to solve here. I have this word, tanger, tanger, I don't know how to pronounce it, so I want to put it through my model, and I want to know exactly how to pronounce it. And I know what these phonemes mean. So is it tanger? No, it's t-e-ng-er, so it's tanger. And that's what we want this model to do. So what we're going to do is basically you can import CNTK modules by name and things like this, but for simplicity here we're going to just import all of CNTK as C, and then we'll explicitly reference things that we're going to touch. If you happen to be following along, I don't know if anyone is, hopefully you have already, well, you can download the data now. It's not so big, so you just need to run this cell. I think it's at most maybe 10 megabytes, something like this, 30 megabytes maybe. So let's look at a real-world example of the data. So this is the CNTK text format reader format. This is one sequence. So each one, each time step is on a single line. And we know that it's all part of sequence 0 because there's this 0. These are a sparse representation of the input words and the output words. And this is a comment. So you don't need this. So a bar and then a hash sign is a comment afterwards. So this is just so I know when I'm looking at this data what it represents. So here is another example. Abadi, so it's pronounced Abedi. And this we're going to use as we're training the network. We're going to keep on running the input through the network and seeing what it's outputting to see how it's training. So let's see. So the first thing, Clemens talked about readers. So one way I could pass all the data into my model is by just loading it up in a file, turning it into NumPy arrays, and writing my training, and grabbing my features and my labels each time. But there's these really nice, basically, readers that do all sorts of things for you. They're written extremely efficiently, and they automatically do proper randomization for training, which is obviously important. And so basically what we do here is we're using the CNTK text format reader deserializer, and it's pointing to the field S0 and S1 to point to my features and labels. And so as you saw, the field S0 is my features, so my inputs, and S1 is my labels. We also have to give the shape. So I have the input vocab dim and the label vocab dim. When you're doing machine translation, for example, you would always have a separate vocabulary because so many of the words are different. Here we're going to use a shared vocabulary just because it's easier. It's very small. So once we have this train reader, this is basically an object that points to our reader and can get our features during training. Here we're setting two layers. So when I mentioned we often use stacked recurrent neural networks, layers of them. Here we're basically using 2 layers for the encoder, 2 layers for the decoder. The hidden dimension is the size of the vector of the hidden state. So if you set your hidden state to be a vector of size 10, then it'll be extremely hard to learn anything because you're trying to squeeze a lot of complex information into a tiny space. If you set it to 10,000, not only will you probably run out of memory, but you will overfit. So there's too much room to store the learned representation. And so typically what's used in these RNNs is somewhere between 128 and up to 2048. And so all of these are hyperparameters that you tune and are very specific to the data at hand. I say use embedding. So what we're going to do is, if you know about word embeddings, something that can help is we're going to basically pass our high dimensional one-hot vector, which represents a word, into an embedding which will return a lower dimensional dense vector that represents that word. And so that can help for a number of reasons that I guess if you come to the next meetup, you'll learn more about. Okay, so let's talk about the actual definition of the network. So Clemens mentioned this key concept in CNTK about dynamic axes. There's static axes, which are kind of the traditional axes that represent a tensor shape. And so you, in an image, for example, you have 3 axes and they're static. It's the width, the height, and the number of color channels. With a dynamic axis, you have dimensions that are not known until the variable is bound at computation time. And so what this means in a recurrent neural network such as this one is that we might have some input sentence which is 5 words long, and then the next input sentence, which we want to run through the exact same graph, will be 10 words long. And so what we provide, instead of forcing you to say, okay, set some maximum length and then pad the rest of it, we're just going to have a dynamic axis, and it's going to figure that out for you at runtime. When we're doing sequence to sequence, we're going to have 2 dynamic axes. One represents the input sequence. One represents the output sequence. Because as should be obvious, the output sequence does not necessarily have to equal the length of the input sequence. Okay, so the way you do this in CNTK, well, one of the ways you do this is by calling an axis. And this is basically creating a new dynamic axis. So we have one for the input and one for the label. Then I'm going to create these types, which we'll use later. The input sequence is basically a sequence over the input axis, and the label sequence is a sequence over the label axis. So this is one of the functional arguments. This is a representation of this functional versus non-functional argument. Okay, so we have basically the building blocks defined for what we want to do. This is kind of what we want our network to look like. In our particular case, we said the number of layers was 2. It could be 3. And basically what you do is you run a word at a time through the first layer of the encoder. Its output, so its hidden state output here, is the input to the next layer, etc. The top layer is what we run the attention over. So those are output hidden states of the encoder. And then the decoder, the bottom layer, attends over those states, has some output and through all the layers, and then through a dense layer at the end, and outputs are generated words. Okay, so let's go through. This is kind of the meat of the tutorial. This is the function. Basically, here we're binding as little specifics about the data as we can. We're not binding as much as we can at this point. So this is really a skeleton graph that once we have data that runs through it, all the shapes will be inferred as much as possible. So let's start with the encoder. So we call this Python function create model, and this will basically return a CNTK graph. The first step is we're going to run our input through an embedding. And so what this does is we call the CNTK embedding layer. We have some embedding dimension that we want our dense vectors to be. And it returns a function called embed that any sequence that we put inside of it will return all of the words in their dense representation. Okay? Now, we have this. In the layers library, there's this concept of default options. So you can have basically a block of code, and you can say, I want everything that follows to follow these specific options. And so for our encoder, we're basically going to use this sequential layer. And what that means is I want to sequentially apply the following functions. And so any data that goes in is first going to go through the embedding layer. Then we're going to stabilize it. Then for the number of layers that we have, we're going to run it through a recurrence. And that's it. And the output will be the output of the very last function that was applied. Now, the reason that we separate this last recurrence out is if we're using the basic sequence without attention, which I said we'll take the last hidden state and send it as a thought vector to the decoder, we use the concept of a fold. So a fold is kind of like a functional programming term, and it's basically provide a function that takes some input and folds it in on itself and gives kind of like a sum, sort of. But in a recurrence, the default behavior of fold is to return the final state. Otherwise, we use a regular recurrence. So that's right here. So this is for attention, and that means return all the hidden states, because we're going to need to attend over them with our attention model. So encode now is a function that we would pass data to, and when we pass data to it, that data would be run through these functions sequentially. Okay. So right now, nothing has been executed. It's just we've just set up some functions. Next, we're going to set up the decoder. Again, ahead of time, we'll set up some functions that we're going to use. So we use this stabilizer here. It's not required. This basically adds a scalar to the training and can help. It's an additional parameter to learn and can help convergence in recurrent neural networks. So that's why it's there, but you can kind of ignore it. So we set up our recurrence blocks. We're using an LSTM. So you could use a vanilla RNN. You could use a GRU. Do people here know what LSTMs are or GRUs? Does someone not? So a GRU is a gated recurrent unit. So LSTMs and GRUs can be seen as drop-in replacements for the vanilla recurrent neural network, but they have some properties that make them easier to learn. So the problem with a straight RNN is that you often have problems with the gradients exploding or vanishing because you're multiplying the same number over and over by itself because of the shared parameter phenomenon. If you think of it in a very simple 1D case where you have and your number is less than 1, if you multiply it by itself many, many, many times, it'll eventually go to 0. If it's bigger than 1, if you multiply it by itself many times, it'll eventually go to infinity. And so an LSTM and a GRU help deal with this. Okay. So we have, and then we have our final dense layer. So here we're setting up a function that applies the final dense layer. If we're using attention, we have this built-in attention model. And here this basically will set up a function where we give the current decoder hidden state and the hidden states of the encoder, and it applies that formula that I showed before. So it basically, it computes that probability distribution, and it creates the weighted sum over those encoder hidden states, and it gives you back this augmented new decoder hidden state. So now here is the actual decoder. And this is what you actually use in the network. So we return this, decode. This is the function. So the first thing we do is we call our encode function that we set up above. So the input that we have, we encode it. So now we have these hidden states. We get the history. So the history during training will be the labels, because during training you know exactly what words the decoder is supposed to output, but during evaluation you don't know yet. You don't have the history until it's been created. So later when we do training, this history will be set to the labels. When we do evaluation, it will be set to the output of the network. So we embed it. So all of our words are put into this embedding space. We go through the layers. If we're using attention, we get our augmented hidden state by calling the attention model. We splice it together with our input, and we return this recurrence block, which is an LSTM, with our augmented hidden state. Basically, then we put it through our dense layer, which we set up here. This projection out is right here, and that's it. So this is basically the overall graph of what the encoder, decoder, dense layer looks like. So this is kind of an abstract model that has to be wrapped first, because as I said, you need this history, which during training is the labels, and during evaluation is what the model has produced so far. So how do we set up training? Our model was created up here, and it's called S2S model, sequence to sequence model. And if we want to create a training model, all we need to do is we say our past labels, so our history, we pass through a delay layer. We set the initial state to the sentence start token. So this is this S that I showed that you use to prime the decoder. And we return that model with past labels, so that's our history, and the input. We're also going to create an evaluation version of the model, because we'll use that just, I mean, you would use it eventually, but we're going to use it now because during training, we're going to sample from the model and see how our model is doing as it's training. So what we do here is we again are going to call the sequence to sequence model, and our history here is create, so this is like the real functional programming stuff. We use an unfold from, so basically we say history is going to be what happens when you apply the sequence to sequence model with the input and history and pass it through a hardmax. We pass it through a hardmax because the output of our model is a posterior probability distribution, and we're doing a greedy decoding, meaning at each step we'll take the most probable word. So hardmax means give me the index of the word with the highest probability in this vector. And so we pass it into the hardmax, and that adds on to the history. And so here, this is how you're kind of creating some, well, labels, if you will. So the first step is always the sequence start token. So that's when you don't have a history. So that primes it to generate its first output, and you take that, and that output is fed back into the model. Okay, so because we have unlimited time, I've been skipping some stuff that you can go through on your own, but I mean a lot of this is boilerplate, besides the function there itself. But basically here, since we have our model, now for training, we have to execute it. So we get Z, model is the input and the labels, because we need that ground truth labels during training. And we set up our criterion function. So this is cross entropy with softmax. So this is basically our loss function. And it's the output of our model and the ground truth. So during training, we call these functions that we set up above. So we have our training version of the model, and we have our greedy version of the model. In this case, we're using a variant of the Adigrad learner. You could use Momentum SGD or Atom or anything here. And this is the training loop. So for some number of epochs, we're going to call the reader and say, okay, get our next mini batch. We will provide this data. And we call train mini batch, we pass in the arguments that the loss function expects, which are the features and the labels, so it can compare where it's got error. And so this is kind of all the magic behind the scenes, where it evaluates the model, it calculates the gradients, and updates the parameters given those gradients. And like that, we train the model. Now, the interesting thing is we're using our evaluation version of the model that we created, model greedy. So during every eval freak, which is like, I don't know, 30, something like, or 100, we're going to sample this same input and see what the model is outputting. Okay? Is anyone following along with the notebook, by the way? And you're executing them? And it's working?
Yeah, the first example that was expected the number of Feedforward because the training set was small, but we were getting
Okay. 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 So once we've got that, so a bunch of things we can skip. So once we have all this set up, we create the model and then we call train. In this particular model, we have 7.5 million parameters that it's learning. And right away, so this is our input sequence. It includes the start token, ABADI, and the end token. And the first attempt before it knows anything is the output is just an end sequence token, because it's completely random. So the training progresses, the loss starts going down, but, and after this very small amount of data, we save the model, and we get some low metrics. So this means 84.3% error, which is not very good. But if you train it for an entire epoch, which I did ahead of time, so on this Surface Book, which has a GPU, but a small GPU, it still makes a big difference. It's about 10 times faster than on CPU, and you can train one epoch in, I think it's like 20 minutes, something like that. And after just one epoch, we get an error of less than 10% on the last. So overall, 24%. So what does this mean? We can now have an interactive session. So up here, if you go through it afterwards, this shows how to test on your whole test set. But what will be more interesting here is doing an interactive session. So we have this model that I trained for just one epoch. We'd have a really good model if I trained for, let's say, 20 epochs. So that might take, I don't know, 5 hours, something like that. And now we'll just call this. So enter one or more words to see their phonetic transcription. So I'll say hello. It says h-e-l-o. So hello. So it works for that one. And the interesting thing is that we also visualize the attention window. So what this means is when we produced this HH, most of the attention weight, so this probability distribution, was on the sentence start token, which might seem kind of weird, but there you go. Now this is a good example. So the sequence end token put almost all of its weight on O, because it knew that given everything that happened before, having H-E-L-L and then having an O, you almost never have anything after it. And so that's kind of one way to see how these attention weights make some sort of intuitive sense. Let's say, so I don't know, psychology. This is one I showed in the slides. So I believe that in the slide that I showed, I had like a fully trained model, and here we have psychology, which is actually a bit wrong because it's psychology, whereas in our PowerPoint, when I had the fully trained model, yeah, we had this AY, psychology. Oh, maybe it's the same. Okay, so you can play with this, of course, and you can have a better version of it by, for example, when I went to train it, I said, train reader, so train, I passed in all this stuff, and I said max epochs equals 1. So as I said on the Surface Book GPU, that took like 20 minutes. So if I trained it for 10 epochs, I just do that. It would save the model, and then try it out, and we can get with this particular model almost perfect. So this is based on a paper from Microsoft Research of, I think, a year, 2 years ago. And at that point, it's really an off-the-shelf sequence to sequence that had worked for machine translation. And they replaced like an old model that got like, I think, 91% word level accuracy, which was really complex, used all kinds of really complex things, plugged it into this framework and got basically 99%. And so we might have just passed the kind of peak, but for a while you could get a paper in anything by just taking your data and applying it to the sequence-to-sequence framework because it worked so nicely and everything. But I think we're too late in most of the like nice problems. So sorry if I think maybe I went a bit fast in this, but go through this. I hope you got like at least the high level overview, and you can see the details by going through this notebook, and then try it out on different data. One thing that I've been trying recently is spell correction, which I just played with a little bit, but it seems to be working pretty nicely, and is a much smaller model approach than what is currently used in a lot of production systems. So maybe that would be interesting. And with that, that's all. Are there any questions? Yes. Yeah, so it wouldn't be the same model, of course. Like the same train model, it wouldn't be the same weights, but using the same exact code and just replacing the data, that's a very good example of, I think I've seen a paper of doing like transliteration, something like this, and again with sequence to sequence. So you don't need to change the structure of the network. You just change the data. Yeah, yep. Yeah, so a lot of it is kind of train data manipulation, setting it up. There's a paper, I think, a year and a half ago by Christopher Manning, I think, and they do parse tree generation using sequence to sequence. So their training data is basically the input sentence, and then they've found a way to unambiguously, or they've decided on a way to unambiguously represent a parse tree in a flat output, which can be then put back to a tree, and they beat the state of the art in parsing by just using the sequence to sequence approach. Yep. Yeah, so in the best approaches, there's usually some tricks that they add in, but you can get very good results in most of these. Yep, yeah, definitely. Yeah, there are papers in this. Other questions? Yep.
Have a mic for you, 1 second. Thank you. Can you apply a sequence-to-sequence model also to well, if you use words or symbols, then it's basically integers that you have. If you use a signal and want to translate one signal into another signal, then you have floats as input. Would this also be supported by CNTK?
I don't see why it wouldn't be specifically supported by CNTK. So the model itself, I'm sure there are a lot of things that could be done to fit that into the framework in a clever way. But I mean, some examples are, using digitization. I mean, if you take these floats and put them into some kind of vocabulary, if you will. So if you kind of bucketize them, I guess that would be one approach. But I know that there's also, for example, if you see that data is being generated by some kind of distribution, so if you encoded it as, for example, parameters in a distribution that could put it into some integer form, that might be one way. But I don't know of a specific model that works in that way.
Thank you for the great talk. I have a question regarding the size of the history. You said that in general we are bound to tweak the size of the history, either not to lose data or not to overfit the function that we end up with.
Sorry, I can't quite hear.
Oh, sorry. Yeah, I'll try to get a little louder. So you said when we were talking about the history, we are trying to set up a fixed size and tweak it in order not to lose the data or not to overfit our functions. Are there any tries to dynamically change the size of the history based on the amount of input that is coming?
So you mean the hidden dimension?
Yes, the hidden dimension size.
I'm not sure. Yeah, I don't know.
Okay.
However, I mean, a very common thing that a lot of practitioners will have wasted a lot of time doing is hyperparameter sweeping. So you train a whole bunch of versions of your model and you try a whole bunch of different hidden dimension sizes and you find the one that works best with some held out validation data.
Yeah, all right, thanks.
Yep.
Anybody else? No? Okay, cool. Thank you again for the talk. Yeah, so I think we have like a bit more time, so you can network and mix and mingle basically, and after we're gonna close the demo place. Yes, and if you have something exciting, just like write me and we can make it happen next time. Thank you.